I wanted to spend a little time on talking about functions and relations. Now, when we pair numbers from a domain with a range, we have a relation. There are certain relations that are specific in that they have a condition that for every domain value there's exactly one range value, and those are referred to as functions. And we covered this briefly in an introductory chapter back in chapter 1 or 2. I'm going to just spend a little more time on it today. So a relation is a function, again, stating that every domain or input value has exactly one range or output value. Hopefully those words are familiar to you with. Another way that we can look at this is looking at the function that's been graphed. And a relation is a function of the horizontal axis if and only if no vertical line passes through two or more points on the graph. And we'll get to that in just a moment. Let's go back and refresh your memories a little bit on mapping. When I'm talking about mapping, we're looking at numbers that are paired with other numbers. And sometimes I will actually convert these into ordered pairs to look at them more closely, but this is a visual, and sometimes this is helpful. 1 is paired with 2, 2 with 4, 3 with 4, and 4 with 5. This represents a function because every domain or input value has exactly one range value. If you were to look at them as ordered pairs, and you'd stop and you'd say, well, 1 is paired with 2, and 2 is paired with 4, 3 with 4, and 4 with 5. Each of these has one output value or range value. On my second example, I have 1 paired with 5, I have 2 paired with 5, I have 3 paired with 7, I have 3 paired with 9, and I have 4 paired with 9. It's this representation right here of 3. It has two different output values, and that does not represent a function. I could look at this from another perspective, and I could look at it in ordered pairs. When I'm looking at the ordered pairs, and again, these mappings, these ordered pairs can all be put on a coordinate plane, which is our next direction. We're going to look at the input or the x values or the domain values. And if they're repeated at all, then they must go to the same output. Well, 6 is paired with 4, 4 with 2, 2 with 0, 0 with -2. None of the domain or input values are repeated, so this represents a function. Let's look at the second set. 9 is paired with 12, 8 with 10, 7 with 8, 8 with 10, 6 with 6. I heard and I see that 8 is repeated. But what you'll notice is that it has the same output value. Once again, this is a function. If an input value is repeated more than once, it has to have the same output. The last example in ordered pairs. 5 with 8, 6 with 9, 7 with 10, 6 with 12, 8 with 14. Notice that the 6 is repeated. Notice that it has two different output values, not a function. So this part so far is something we've already covered, just talking about it briefly. If I wanted to take a look at a graph, if I'm looking at a graph and I want to determine if this represents a function, I'm going to be doing something called my vertical line test. I'm going to take a vertical line, and I'll create one here so we can use this as our guide. All right, maybe I should have changed the color on that. I don't know if I can. Is it too late? Probably. Let me redo that. Oops. Let me redo that in red. It'll be a little easier up against the other color to see. So let's just, one moment please. We're just getting this, rid of this one. All right. And we'll get rid of this. And we're good to go. All right, so we're going to take this and to do what we call the vertical line test. We are going to take this line and we're going to scroll across. And each time I stop, I'm looking at this long vertical line to see if there's more than one point that falls on a particular vertical line. And as I'm going through, this represents a function. Let's look at a second graph. In my next graph, if I were to do a vertical line test, and I have a line here already, I'm going to be scrolling along and it looks like there's only one point on each vertical line until I get to this part here. When I get here, I'm noticing that, and I'll change the color so you can see, I'm noticing that there are several points on this same vertical line. That means, let's talk about the ordered pairs there. 1, 2, 3, 4, 5. Well, I have 5, 1 right here, and then I have 5, 2 right above it, and I have 5, 3 above that. These domain values have different range values, so this does not represent a function. It fails the vertical line test because, again, there are several points on that same vertical line. Okay, so there we see that. Fails the vertical line test. So that is another indication whether something is a function or not. And we can see other graphs as well. We see there are several points here all along falling on the same vertical line. Not a function. This one, again, represents a function. This one does not. So we can see that vertical line test coming into play. One last thing I want to discuss would be function notation. When a function is defined by an equation, sometimes it's given a special look or special notation, as I'll call it. Y is equal to 3x plus 2. That's an equation form, and we call that function form. But function notation replaces y with this expression f of x, or f at x. And it's just the name of the function. We don't calculate anything with this. We're using the rule, and we're substituting in values. This one says, let's evaluate this function. Let's input negative 5. So I'll have 3 times negative 5 plus 2. So that gives me negative 15 plus 2, which yields a negative 13. So when we input negative 5, our output is negative 13. Again, this is read f of x or f at x, and simplifying it, it just says that we're going to evaluate something at a given point. F is not considered a variable, it's the name of the function. I have 2 times negative 4 squared plus 3. That will give me 2 times 16 plus 3. So that's 32 plus 3. So 35. So when I input negative 4, my output is 35. And we'll see there are others. Here we want to evaluate this one at negative 2. So I'm going to put f at negative 2. The only thing I'm calculating is what's on the right here. That gives me negative 4 minus 3. Add the opposite will give me negative 7. So f at negative 2 gives me an output of negative 7. One last one here. Let's evaluate at x is equal to 0. And sometimes they'll use g of x as well. So here we have negative 5 times 0 plus 2. So when we input 0, our output is 2. We have 0, 2. And there's other things that we can do with this, and I'll bring those up in our next session where we could have a function rule within a function rule, but we'll save that for our next session. And don't forget, we have a test coming up.